lift aircrafts for serious power level, anything above 1,000 horsepower, the gearbox becomes a necessity. The direct drives are not just there yet. So this is a list of topics that I want to cover in today's talk. So we'll start with the introduction to the basic functions of the drive system in a powered lift aircraft. Look at what the weight trends look like. And then what are the current technological goals for the rotorcraft drive system and associated challenges in maturing these technologies that meet the goals. Then we'll talk about new experimental gearbox architectures that enable very high power density. And here I would specifically talk about the high reduction ratio gearbox technology demonstrator that I've been working on for many years now. Then we'll take a look at component and material level technologies, advanced engines and motors, drive system design tools and methods, and finally, alternative testing approach that enable the industry to bring the concepts to market much faster. Okay, so let's begin with trying to understand the basics of a rotorcraft drive system. Primarily, the drive system's function is to transmit the high speed and low torque power from one or more engines to the low speed and high torque power output at the rotor. The drive system also has these power takeoff routes to drive accessories like generators and pumps. And the other two functions that the drive system serves is to transfer the bending and shear and thrust loads on the rotor to the fuselage by providing a structural path. It also serves as a point of support for these engines. And all of this needs to happen within the constraints listed here. So must be lightweight, shouldn't make a lot of noise in the cabin, must have a very high efficiency, high fatigue life, and time before overhaul, low manufacturing costs, and must also be able to transmit power when you have loss of pressurized lubrication. Right. For the multi-rotor aircrafts, the drive system serves a few additional functions. So take, for example, the AW609 tilt rotor. The drive system must enable continued power transmission during this conversion from the takeoff to the full airplane mode. Right. So this means that the entire prop rotor system, prop rotor gearbox, should be able to tilt about an axis so that the rotor mast axis is always aligned with the rotors on both sides. Okay. All right. Also, this drive system needs to continue delivering power in case engine on one of the nacelle fails. So you still want to drive the two rotors at same RPM, even if the engine fails. And for this, need to have a mechanical interconnect between the two gearboxes. Right. The final function that the drive system serves in a multi-rotor aircraft would be to split the powers, the symmetric power delivered by the engines to differential power at the rotors that enable you to maneuver the aircraft. All right, now why drive system design consideration is important? It's because the drive system, entire drive system, along with the main gearbox, dynamic components, and the housings, can take up as much as 20% of the empty weight of the aircraft. Right, so all clean sheet designs need to consider drive system architecture from the very beginning. This table here lists out the weight of main gearboxes only for some of the helicopters from different classes of power. And as you can see, as you scale up in power, the drive system weight, the main gearbox weight as a percentage of the empty weight only goes up. The chart to the right here shows a further split of this gearbox weight. And what you would find is that out of the main gearbox, the bulkiest components or the bulkiest subassembly is usually the final reduction planetary gearbox that sees the highest torque levels. Okay. All right. Now, if you try to fit the weights and try to get a trend out of what the drive system weights look like for different helicopters, you get a trend like this on a log plot, which shows the drive system weight on the y-axis. And on the x-axis, you have the horsepower divided by the output RPM. So this is a measure of the output torque. Okay, now with technological advancements, advanced rotorcraft technology programs, we've been able to get off this trend and save 23% in weight. But it doesn't quite solve the problems around gear noise and reliability. Okay, now here we try to show where the multi-rotor aircrafts and land on this chart. As you would expect, the drive systems for multi-rotor aircrafts are heavier compared to equivalent helicopter in the same class. But consider that you are buying a lot more in performance by increasing that little weight. And also a lot of systems are duplicated and there are mechanical redundancies, but the performance is worth it. So on one end, you have the eVTOLs and personal air taxis, which are usually 250 horsepower class vehicles. And on the other end, you have something like large civil tilt rotor concepts with as much as 20,000 horsepower of installed power and the same height ceiling as a commercial airplane, which can carry up to 100 passengers with the luggage. So this is still in concept stage, and most of these aircrafts listed here are at different levels of technology maturation. Right. So a lot of ongoing R&D in rotorcraft drive systems today aims to achieve these three technical goals: make the transmission as compact as possible by reducing the number of gear stages, and almost try to double the power density from the state of the art. All right. And then also lay out the components such that it helps you optimize for low weight and reducing the complexity of the entire drive system. Okay. Finally, a lot of work, a lot of research goes into improving the performance and reliability by extending the fatigue life of the components, early failure detection techniques, and just using better design methods during the design phase instead of testing entire gearbox and making improvements later. So getting the design right first time. And what makes it really challenging is that very often these three goals are in conflict with each other. So let's begin with taking a look at some of the alternative drive system architectures that have been in development over last few decades. Okay, So at present, if you look at the helicopter gearboxes, they have a single fixed speed ratio between the engine input and the rotor and the output at the rotor. But in helicopters, the rotor speed during the hover is higher than when it's cruising. So this slide here shows a concept for the so this shows a concept gearbox which would fit in the earlier stages of the gearbox, meaning closer to the engine at the low torque, high speed side. And what this configuration lets you achieve is a change in speed. So when you engage this clutch, this is a direct drive from the engine input to the output of this little gearbox right here. And when this clutch is disengaged, the power is routed through these gears and you get a speed reduction ratio. So this kind of architecture enables you to have two different speeds while maintaining a single engine speed. So you don't have to vary the engine speed anymore to get the required speed output at the rotor. And this leads to gains in efficiency, but at the same time, it comes at the cost of adding some weight. This concept also features some new technologies like rotating oil-free feed-through mechanism, which we'll talk about in later slides. All right. The gear trains that allow very high reduction ratios are also very significant interest to the community. The most you can get out of current planetary gearboxes is about 4:1 reduction ratio. But with gearboxes like compound planetary and pericyclic drive, you can get much higher gear ratios. So this allows you to eliminate some of the stages, right? So going from 3-stage gearbox to a 2-stage gearbox is made possible by using a high reduction ratio. And it allows you to also use a smaller high speed motor if you intend to use electric power with a very compact gearbox, providing a high reduction ratio for the rotor stage. So let's look at these two gearboxes a little bit more in detail. So here are the two proposed HRT solutions. HRT stands for high reduction ratio transmission, the compound planetary, and the pericyclic drive. So, all right, I'm trying to compare the two drive systems here. In a compound planetary, you get speed ratios of the order of 15:1, and that is achieved by using a larger planet gear meshing with the sun gear, and a smaller planet gear on the same shaft meshing with the ring gear. So this gets you a higher speed ratio, but at the same time, you're splitting the face width on this gear, reducing its stress, bending strength capabilities, and you're not getting much advantage in the weight, in terms of weight. Also, you have 1 to 3 teeth in contact per gear mesh, which leads to higher mesh stiffness variation. Now, some of these shortcomings are addressed by the pericyclic drive architecture. So think of this gearbox as a 3D generalization of the parallel axis planetary gearbox. Here you have an external and internal bevel gear mesh at a very large shaft angle. And what that lets you do is bring in large number of teeth in contact well beyond what's described by the involute line of action. So as you load it, the more you load it, the more teeth come into contact. So with that, that enables you to have a small mesh stiffness variation, lower excitation during the lower excitation during the operation of this gearbox. And within a very compact architecture, for example, this one shown in, enables you to have a 32:1 reduction ratio going from the input to the output. So in this animation, the bodies are sectioned, just to show their relative positions in space as the input shaft rotates. Okay, so my work was on building a technology demonstrator for the pericyclic train. And the goal here was to design a 100 horsepower prototype that can be tested on an existing test rig. For example, this one shown here. And what we did here was build a design framework that that enables you to achieve that goal. Enables you to build the technology demonstrator. So we begin with first determining the design space available to us from test rig. Look at the parameters such as input speed, output speed, rated torque. Do some initial calculations for the required gear ratio, and come up with a possible number of teeth. Really try to determine the design space. Next, we narrow down this design space through a series of modules, starting with looking at how the load flows through the mechanism and what is the load taken up at each joint in this mechanism. Right? And from these component level loads, we take a look at what is the stress developed on each of the single components. All right, now this is where we needed to build design tools from the ground up, from first principles, because no standard tool can currently handle the kind of contact and the 3D loads you see in this drive system. Okay. Now, once you have sized the gears, selected the right bearing from a catalog, or designed them, we check all these designs for assembly. Meaning, once these components are sized or selected from the catalog, whether they will fit together into assembly and actually function. So what you end up with is a set of design points that show you the compromise between the efficiency and the weight. So we just went ahead with the lightest design. And this is followed by a dynamics analysis to do an eigenfrequency survey and check that they are outside the operating speed range. Okay. And once this is acceptable, the design is further matured, the drawings are produced and sent out for manufacturing to get a prototype. So with this framework, we were able to mature this HRT concept into a 100 horsepower prototype that was designed for testing. And these pictures here show the components and sub-assemblies as they were manufactured. This is a video from no-load testing, which was completed at Penn State very recently. And it shows how smooth the drivetrain is. It shows only one side. So no hard contact between the gears or edge contact was noted. And it was working as expected. Right. The next step in the design, once all the tools have been validated using the 100 horsepower prototype, is to scale up this design for a higher power. So this shows this chart here shows the compromise between the efficiency and the drivetrain weight for 300 horsepower, for 300 horsepower level. And as you can see, it gets very close to the state-of-the-art drive systems in terms of efficiency and weight. Okay, some more results for the from the design tools that were developed during the design of this drive system. So what's shown here is how the contact stress changes on this gear mesh as you increase the torque through this drive system. So 3 teeth are shown in contact, and as you increase the power, there's still 3 teeth in contact, but the stress on each of these teeth increases. But when you look at this gear mesh, not just the stress on the teeth, but also the number of teeth in contact increases. So what we are trying to do is validate some of these analysis results from the actual experiments ongoing. Okay, another very important parameter for the dynamics analysis of the gearbox is to understand how the stiffness of the gear contact varies as you rotate this gearbox. And these plots here show you the variation in the mesh stiffness, the stiffness of the contact. Now for spur gears, this is usually up to 50%. But here it ranges between 20 to 30% based on what the torque input is. Right, and on the right-hand side is shown the transmission error plot, which serves as a parametric excitation in the gearbox, and it tracks with the speed of the gearbox. I won't go much into details for these results. Okay. Right. Finally, talking about the bearing design for this gearbox. Comprehensive tools for designing the bearings under application of complex 3D loads and gyroscopic loads were developed. And very recently, we presented a paper in the Vertical Flight Society Forum, which was awarded as the best paper in propulsion. So this work was done with Nick Weinzapfel and Nathan Bolender from Sentient Science. And with their tool, we were able to model these bearings as flexible bodies and look at what the contact stress on this roller looks like as it rolls through the inner race. So this is the inner race unraveled on a from it's the 360-degree inner race unraveled from -180 to 180-degree position. And what's shown here is the contact stress on the roller at different positions along this race. What we noticed here was that at some positions, there is loss of contact of the roller and the ring. And in the bearing world, we try to avoid that just because it leads to skidding and reduction in the fatigue life. So to do that, you can apply higher preload. And then Nick was also able to run a contact fatigue simulation and actually do viable plots for the bearing lives. So with a higher preload, you have a lesser probability of failure. And that buys you more fatigue life. Right. So on to the next concept I want to highlight here, which is the magnetic gearing. And the reason why I want to talk about it a little bit is this kind of gearing has a potential to be easily integrated with electric motors. But it's at very early stages of development. The idea here is to achieve the same gear ratio by using electromagnets instead of contacting rolling elements. So the pros here are that you don't have to deal with contact. No contact means don't have to deal with lubrication. Then it would be low maintenance. You don't need to spend a lot of money in maintenance, and potentially there would be low vibration too. But at the same time, the temperature limits for these magnets pose a limitation on how high you can go in the power and speed. Also, the individual magnet interaction is weaker than actual contact with. So, the team at NASA Glenn has come along far in developing the prototypes and increasing the power density. But it's a long way to go from here. It's a great candidate for integration with the electric motors. Okay, newer materials are also enabling increases in the power density compared to the baseline 9310 steel materials, which are used for aerospace gears currently. So these new materials offer you higher fracture toughness. New materials meaning new kinds of steels produced using different methods like vacuum induction melting, vacuum arc remelting. So these kind of steels have a very high core hardness, have a higher fracture toughness, and also have a very high hot hardness. So if you look at this plot on the right-hand side top, it shows you how the hardness of steel coupon decreases as you increase the temperature. So for a 9310 steel material, it falls off after 200 degrees Celsius, right? But for certain new steels, they can retain their hot hardness up to a very high temperature. All right, what that enables you to do is to drive your gears at much higher speeds, meaning the pitch line velocities can be much higher. The gear surfaces are allowed to rub much more at a higher sliding speed. You can afford to have higher temperatures on these gears without compromising on the strength, the bending, scuffing, and the contact fatigue strength of the gears. Right. The plot here below also shows the ability to retain the compressive residual stresses, which improve the strength of these gears in bending. Okay. Non-metallic materials are also making themselves useful. So in this picture is shown a large gear with a steel rim and steel teeth, but with a composite web. So instead of having a steel web, the web is made out of a composite material. And that enables you to save a lot of weight and also, probably it's greater. It's better with it's better with at higher speeds. Okay, but the issue here is delamination of the composite material and the adhesive strength at the interface. So there is a lot of work ongoing to optimize the interlocking features here to enable higher to enable higher interlocking between the steel rim and the composite web. Right. Ceramic rolling bearing elements are again great with lower lubrication. Also, ceramic rollers are lighter than steel rollers, so you can get weight savings. You have to carry lower level of lubricant. The drawback here is that they fail faster once the failure initiates, and you have to deal with higher contact stress. With additive layer manufacturing, the design options are pretty much endless, and you can make the casings of the gearbox as one single complex piece, and also have space to put the coolant in. So these kinds of concepts are also in advanced stages of development. So a lot of good opportunities here. Right. I'll talk a little bit more about the component level technologies here. So surface treatments like nitriding and DLC coating and super finishing also enable you to have higher contact fatigue strength, and are a huge benefit, especially in dirty environments. So this chart here shows how the component lives can be improved by surface treatment, having a better surface finish, or nitriding your surface to make the outer case harder and have higher residual compressive strengths. Right, so it's not just gears and bearings, but all the other mechanical components are also seeing a lot of advances. So, for example, shown here is a composite drive shaft for a helicopter, connecting the main gearbox to the tail rotor. It's usually a very long drive line, and the idea presented here by Airbus is to have a hybrid metal composite drive shaft. So the shaft is usually made out of composite, but towards the end, you have to put a piece of metal in just to have a better interface or interconnect with the coupling and the next shaft. So the idea here is to do away with the fasteners completely at this interface and have this metal piece welded into the composite shaft. Right. These are some of the new advanced couplings which could be used in long shafting systems. They enable you to have a very high degree of misalignment while still maintaining the strength of the drive line. So you could have parallel as well as the angular misalignment capability in this drive line. Okay. Another area of interest is driving the composite shafts at high supercritical speeds, meaning beyond their first critical or second critical speeds. And the enabling technologies here are the dampers. As you traverse through the first critical, the damper must be able to drive down the amplitude at the resonant frequency as you cross it. So with supercritical shafts being driven at high speed, you can transmit much more power with a smaller shaft. So that's the reason why we're looking into something like this. Right, a lot of advances in the lubrication system too. Increasing the efficiency of lubrication has a direct effect on the weight, because now you have to carry a lesser amount of oil to achieve the same amount of cooling. So here I want to show you some of the innovative oil delivery mechanisms. The planet gears and the bearings on a rotating carrier are some of the hardest components to get into as far as lubrication is concerned. So this picture here shows a schematic of a rotating feed-through mechanism where oil is fed into a stationary oil jet into a stationary housing. But right here at this interface, it's transferred into a rotating shaft. So transfer of oil from a fixed frame to a rotating frame, and then it's pumped through the shaft and then there could be capillary holes at different locations along the shaft to deliver oil to the components hidden behind. Another method to increase oil delivery efficiency is to use the oil scoops and the distribution grooves. So let's say you have a bearing hidden deep inside behind a structural element, and you want to get oil to this bearing, but a direct jet is not possible. So what you can do instead is impinge oil and let the scoop pick up the oil, and then through this distribution groove, route the oil directly to the roller. So this is called as under race lubrication, and it has a very high efficiency of delivery of the oil, greater than 95%. Right. And then, of course, there are more options around having solid lubricant and doing away with or somehow compensating the lack of the oil itself. So the cages of these bearings are made with materials that can serve as lubricants in case of extreme events. So delivering oil with the higher efficiency enables you to fly further and faster, and that is critical for loss of loop performance. Okay, the new engine architectures enable you to maintain a very high efficiency and performance under different speed regimes. Now, remember we talked about how the rotor speed needs to be different during hover and cruise. Now, these new engines are optimized to deliver you the performance and the efficiency under two or three different speeds instead of being optimum only for one single speed. So a lot of opportunities here too. Right. Finally, let's address the electric motors. So yes, it's true that the electric motors used in aviation have much higher power density compared to any other system. But I want to draw your attention to this chart on the right hand side, which shows, so if you use, so let's say you have, you're trying to design your drive system and you're trying to pick between whether I should use a direct drive or use a motor plus gearbox combination. So what this chart shows is that if you use a direct drive, you end up with a much higher weight. But if you use a motor, a smaller motor with a gearbox, you can drive down the total weight of the system. So for this particular application, a gear ratio, a total gear ratio of 12 in conjunction with this motor is probably where you see the maximum benefit. And after that, the curve just flatlines. So whenever someone, if someone wants to make an argument that direct drive is beneficial, this is the chart that I usually like to show them. As you scale up in power, it makes much more sense to have an electric motor followed by a gearbox. Right. Computational design tools for the gearboxes have also come a long way. Today, we can predict the gear contact and bending stresses with much higher accuracy, study the dynamic characteristics, and even run many cases to cover the entire tolerance band of, entire tolerance band from your manufacturing drawing. Rotor dynamic tools have also, matured quite a lot. But there is still some gap in doing rotor dynamics for the composite shafts. Now, with the advent of multi-rotor VTOLs, the needs for advancing these design tools is only growing. So one such effort that we have recently undertaken is to understand how torsional dynamics of the drive system of a tilt-rotor aircraft affect the loads at the component level. Meaning, what should be the dynamic factor we must use while we are designing these individual component gearboxes. Okay, so as I explained earlier or mentioned a little bit earlier, the helicopter, uh, conventional helicopter, is a multiple input and a single output system, meaning you can have one or more engines, but the output is delivered as at the single main rotor mast. But the tilt rotor is a multiple input and multiple output system, meaning the output is delivered at two rotor masts. Okay, so this picture here shows that if the aircraft is flying symmetrically, if it's hovering symmetrically, you would have same thrust delivered on the two rotors. But let's say there's a lateral gust. What the pilot will do in this case is pull hard on the collective stick and try to get more thrust on this rotor. So you're still drawing same symmetric power from the engines, but you have differential thrust on these rotors. So in this case, what happens is some of the power is rerouted from this gearbox on the right-hand side into the left-hand side gearbox. So this maneuver is called the differential collective pitch. And the tilt rotor or multi-rotor gearboxes must be designed for this peak asymmetric power and not just maximum installed power divided by 2. Add to that,
Dr. Tarmay, there is a request to repeat the last slide again. Okay, some.
Sure. Okay. Is there anything specific we want to talk about on this slide?
Yeah, actually, this. Can you please unmute and really comment on what exactly you want to be repeated?
Yeah, please. It's regarding the tool design. Just with the previous slide. Just.
Sure. Yes. Sure. So what I was saying here is the tool design, computational tool designs have enabled us to predict the gear contact and bending stresses with a very high level of accuracy in the design phase, instead of having to go to an actual test bed. So these tools are all validated by actual tests, by the way. So anything specific you want to know here?
I guess we can continue further.
Okay. All right. So as I was saying, the gearbox must be designed for this peak asymmetric power, as well as what goes on. As well as take into account the torsional dynamics, the complex torsional dynamics of this entire drive system. So what you're looking at here is a 3-level problem, which needs to first, so you need to first find out how the torque oscillates. What's the torque response? What's the torsional response of this entire drive system? Then understand the torsional dynamics of the planetary gear stage, and then look at how the load is distributed on each of these single planet gears. So this is what we are trying to estimate, meaning how to model the system level torsional dynamics effect and study its effect on one single component. So the output, the result here would be to derive a dynamic factor for application during design. And to that end, we have developed our own in-house cylindrical gear analysis program, which can accurately predict the contact and bending stresses on each of these gears given a certain position in time. All right, I won't go through much details over here, but this picture here shows how having slight misalignment can bias your contact to the positive Z face of the gear. Okay, it's also important to have tools, like I was saying, it's important to have tools that tie the system level dynamics to the reliability of the components. So digital twin, which is made by Sentient Sites, is one such tool that lets you look at how the system level dynamics affects the loads on the gears and bearings, and then finally predict how a crack will nucleate with the minimal amount of sensor data. Another one is the General Electric Bayesian hybrid modeling analysis, which is a probabilistic mechanics framework. And this goes even one level higher and gives you the probability of failure of an asset operating in the field. And what that lets you do is enable the optimization of service interval and much more robust tracking of the assets deployed in the field. So I think we are running out of time. So, all right, I'll quickly breeze through this last section. This is the final topic of my talk, which emphasizes the alternative approaches in gearbox testing and how to bring the concepts to market faster. So a traditional test sequence, what ends up happening is assemble the gearbox and do increasingly complex tests until it's validated and ready to be integrated with the aircraft and sent off to the customer. But at each step, the cost of failure increases. And if, let's say, you pass all these tests, but fail right here, there is no way, I mean, it would be very hard to identify the root cause. And what ends up happening is you would have to go back to the drawing board and look at all of the gearbox components. So that can delay your entry to the market. But with these new model-based system engineering tools, it's possible to study the dynamic response, the contact patterns, and these are already very much validated with the experimental analysis. So it's possible to get the design very close to what you want the first time, like without having to go through the iterative testing. So leveraging these model-based system engineering tools and an alternative testing approach, wherein you begin testing the components in subassembly prior to assembling the gearboxes. So in this alternative approach, you assemble two gearboxes, not one. So the one is on an attitude test rig that enables you to simulate the gearbox being on the wing of an aircraft or different attitudes in the nacelle in case of a tilt rotor. Right. And the other test rig is a TRL5 rig that allows you to test the full gearbox assembly. And during this test, the lab tests are going in parallel for component and subassembly. So let's say if you see any issues here, what you can do is compare them to the lab test results and then reconcile the two of them. And there is an opportunity to identify the root cause earlier and replace the component or the problematic subassembly early on before you move on to the flight test and certification test. So the benefits of this parallel testing is that it lets you find and resolve the problem sooner, compresses the work schedule. You can put in higher loads with much less risk and expand the design envelope maybe. There's also faster turnaround for problem solution, and it's much more suitable for incremental testing and using novel lubricant formulations. The challenges it would include much higher upfront cost with the setting up of multiple test rigs. The program management becomes complex, and the boundary conditions are not exactly replicated. And also, you need a much technically skilled workforce to implement a program like this. But a well-executed test program can greatly accelerate your concept to market development cycle. So that's all I have for today. I know I covered a lot of different topics here, but all of these tie to one single objective: increasing the power density and reliability of the existing and the new gearboxes. So with that, I would thank you all for patiently listening.
Thank you, Dr.
If
Mathur.
any
It was
questions.
really amazing presentation, and I really enjoyed. I mean, all the extensive coverage that you made. I mean, of various state-of-the-art activities going on in this domain. I'm sure. I mean, Dr. Kota Harinarayana sir. I mean, I hope you are there. Okay? You would have definitely enjoyed this presentation, and the kind of approach is there. Okay? So, sir, I mean, you have any questions or comments?
I think this presentation of Tanmay has been extraordinarily good. It has been a great learning experience for me to what extent we can, the developments are taking place, and what all the tools that have been developed, what all the levels of TRL levels. And I'm also happy to see the embassy techniques that could be deployed to reduce the cycle time and also increase the confidence level. And he is also talking of parallel testing, which looks good, but you also have a worry about what its plus and minus points. In fact, I find I was so happy to listen to Tanmay. Thank you very much for this extraordinary,
Thanks for the kind
beautiful
words.
talk.
Thank you.
Dr. Vijay Kumar sir, I mean, you have any comments, sir? Or
yeah, it was a very good presentation. Thank you, Tanmay, for very good presentation. I have only
Thank you
one
for
question.
listening. Yes.
See, is it good to have more stage gearboxes, let's say 3 or 4 stage, or less stage?
I'm sorry, I didn't get the question.
You can have you have to anyway reduction gearbox. Sun and planet.
sir, your voice is breaking, sir. Actually.
Yeah, you can have more than one stage gearbox. Okay.
Yes.
Is it good to have more stages or less stages?
Okay, so it's
I
good
will
to
explain
have.
the background. The background to this is that we had one of our projects, which I don't want to do it now.
Again, we are not able to
Probably
hear you.
less stage gearbox, where the torque that we had was very high. We got into some problem. So what do you think? To have a torque reduction ratio, less or more, which is better?
Yes, so right now, with the material and the design capability we have, the optimum number of stages works out to be 3 or 4. Right. What we are trying to do here is to cut down on that number. It's always good to have less number of gear stages, because then you have lesser mechanical components, lesser points of failure, higher reliability, and just the mode of failures would be different. So yes, having lesser stages is always good. But at the same point, you need to ensure that they can react to the power flowing through the system. So that's what I was trying to show here. Different mechanisms that enable you to put higher power through lesser number of stages or smaller.
May I ask one more
design
question
specs.
to Tanmay?
Yes, sir.
This is, see, all said and done, the helicopter with this, what you call main rotor, tail rotor, and all the things, are fairly complex.
Yes.
And complex mechanical engineering. And today, a hybrid helicopter, a hybrid vehicle,
Right.
unmanned vehicle, so or eventually it will be manned vehicle. where it can vertically take off, and after it takes off, you go into regular normal cruise. It's comparatively simpler. Okay.
Right.
So
Yes.
I find now, earlier I used to see unmanned helicopters being designed, developed and all. But of recent, in the last 10 years, I have not seen a single unmanned helicopter. Either the reason is being because of the complexity, as a result, the cost is high, or any other reason.
No, I think right now we are not there yet as far as fly-by-wire capabilities are concerned. So Bell Helicopters has been trying for last 20 years to certify their fly-by-wire helicopter, but it's just a fact that the kind of redundancy you can get from mechanical systems is unmatched by fly-by-wire techniques. And even in terms of autonomy, as far as I know, in my limited knowledge of autonomy, we are not there yet technologically to fly helicopters which carry these very millions of dollars worth of components. I think might be a long way to go for unmanned aircraft that can carry serious payload and passengers.
Okay. Abhishek, would you like to comment on this point?
Sir, actually,
Of course.
I mean, there is this effort going on. I mean, just in the previous presentation, I mean, we had Dr. Omkar from NL. So he also showed that video of this US-60 made optionally pilotable, which happened only last year, I think. I mean, that was done actually. And Kaman K-Max also have been, K-Max production was closed long back in early first decade of, I mean, this century. But then, I mean, after Lockheed Martin converted their vehicle into optionally pilotable for this hauling of cargo, I mean, it actually, they had to restart the production because there was a huge demand for this K-Max helicopters. So they restarted the production line after it was closed for quite some years actually. And I mean, for combat side also, a lot of things are going on. But yes, I mean, there is still significant dependence on mechanical systems, and it is still way to go for many scenarios. I actually have one question for Tanmay regarding, I mean, for smaller UAVs, for example, variable pitch quadrotors. So I think, again, Kaman has come up with a variable pitch quadrotor for heavy lifting, I think some 100 kilogram cargo or something. I mean, I don't know if it is launched or not, but I mean, I had seen pictures of that and so on Kaman website, and probably also displayed in VFS forum once. So in that, I mean, there is a transmission required because now you have to power 4 rotors from a single engine, or maybe a double engine or whatever. But that is still a bigger scale, I mean, 100 kg plus. We have made a very small prototype where we tried playing with both the gear and this bevel gear kind of setup, top even gear, and other was actually with belt drive kind of thing.
All right.
But now we want to scale it up to a bigger platform where we actually are able to lift 20 kg payload or something thereabout for spraying, pesticide spraying purpose. So engine powered multi-rotor drone, which tries to now compete with these electric powered spraying drones. So what would be so it's a long question, sorry, what would be a good choice for transmission? I mean, do you think belt drive systems are still, I mean, timing belts are still reliable enough and simple and cheap enough? Because the cost will be very critical here. Because if you make it very precise and accurate and the cost goes up, we'll not have takers.
Okay, so I am not very well aware of the advances that have taken in belt drive technologies. But I'm sure they've done some work with increasing the surfaces and modeling the tribology much better. So I'm completely unaware of that space. So I don't know how to comment on it. What I can show you though is a combination. So you might be able to get away with 2 stages, one bevel gear and a planetary gear stage. As far as if a gearbox is an option, if it works out to be an option. So I think that's what Kaman K-Max had in their helicopter too. two intermeshing rotors.
Okay. No, that is, I mean, good point. Actually, even like Mosquito helicopter, which is the small helicopter, they also have this timing belt kind of thing only, which powers the main rotor, because they have
That's
kept it
very, that's very
low.
interesting.
Yeah,
I was unaware of it, honestly.
Okay. Yeah, so you should
Professor
check it out.
Abhishek, I just wanted to comment here when you mentioned about this belt. Actually, there are helicopters which are certified under CS27, which is the normal category, which have a belt transmission. So one example is the Gimbal Cabri. It's a French two-seater helicopter, which you can look up, and they have all the details in their flight manual. It is it has been certified by EASA, and it is the transmission between the engine output and the main and tail rotor gearbox. It's through a belt drive.
Right. So I mean, likewise, I mean, this Mosquito also has the main rotor itself driven from the engine using a belt drive, basically.
I think right off the bat, I would, as you scale up the power, I would worry about the heat and slip, the thermal capabilities of such a system.
Right.
How do you keep it cool? That would be the first thing that would cross my mind.
Okay. So I think we have already run out of time a little bit. I mean, is there any one last question? So before we move to the next speaker, I just make a quick, sort of announcement or information sharing that Dr. Mathur is actually a faculty candidate at IIT Kanpur, and we are hoping that, I mean, he will be joining us very soon. So that, I mean, we'll start a sort of a new chapter in this domain at IIT Kanpur, I mean, which is in the transmission of VTOL systems. So it will open us a new domain of research. So this is some information I wanted to share also. Okay. So thank you so much. I mean, it was a really informative and educative presentation. There are a lot of comments on the chat also regarding that. Okay. And actually, last time when he made a presentation at IIT, I mean, I was traveling and I couldn't see his presentation. So this actually was an excuse for me to see his presentation as well. So it is very nice. Thank you so much again. With that, I mean, we'll move to the next speaker. Let me just share.
All right.
Yeah.
Thanks for having me. All right.
Yeah.
Have a good evening, everyone. Bye.
So the next presentation is by Professor Soumya Ranjan Sahu from Electrical Department at IIT Kanpur. He received his BTech degree in electrical engineering from Veer Sundar Sai University of Technology, formerly called UC Barla, India, in 2008, and MTech and PhD from the SISCON at IIT Bombay. Then he worked at NAL for some time, for 5 months, and then he joined the electrical department at IIT Kanpur, where he has been conducting research in the domain of control of unmanned aerial vehicles, multi-agent systems, coordinate control, and its application to aerospace as well as electrical systems. So with this brief introduction, I'll request my colleague and friend, Dr. Sahu, to give his presentation on this tilting quad-rotor systems, which his group has been working on and made a lot of progress for quite some time. So I will stop sharing.
Okay, thank you, Dr. Abhishek, for this kind introduction and inviting me for this talk. So I'll just share my screen. So I hope the slide is visible in full screen.
Yes, we can see it. I mean, please go ahead. Yeah.
Okay. So my talk would be very brief, and I'll be, as Abhishek mentioned, that we have been working on this tilt rotor, quad rotor for quite some time now. But this is not exactly a new design that we have proposed, but rather we are looking into various control aspects into these quad rotors. However, today I'll be presenting a very simple controller where, and also I'll explain the structure for such quad rotors and how it helps.
Okay, we want to discuss that.
What is the benefit of these quad rotors over the other existing ones? And one of the interesting experiments that we have carried out at IITK with my PhD student here. Okay. So as far as quad rotors are concerned, their control is based on basically the usual rigid body models. And since, as the name suggests, there are 4 rotors in a quad rotor, and hence they are basically under-actuated systems. So what you have basically is, would like to control the position and the attitude of this particular vehicle, but because of under-actuation, what happens, the XY motion of such a vehicle essentially gets coupled to the roll and pitch of the vehicle. So what you can essentially generate as a command is the position and the heading of the vehicle, of which the XY motion gets converted to roll and pitch, as I said, and then the roll and pitch are actually realized by the control laws of this vehicle, which results in this X and Y motion. Now, with a modification in the structure of the conventional quads. So in conventional quads, what happens is the rotors are fixed so that the thrust that is generated is always perpendicular to the body in consideration. So the body here is basically the quad. So the direction of the thrust is fixed. Now, if by any chance, if the direction of the thrust can be changed and it need not be perpendicular to the body frame, so it need not be perpendicular, and we should be able to also change the direction of the thrust, then possibly we might be able to decouple the control of position from the control of the attitude. Okay, so one way to basically do it is, instead of mounting the servos onto the fixed frames, you mount them on basically the motor bases or the propeller bases are such that they can be rotated. Okay, so here we use off-the-shelf servos that are available, and these servos are non-feedback servos, so they run in open loop. You give them a PWM signal, they would be encoded for a certain angle, and they would go to that particular angle possibly. But these servos are very cheap. They are like I think one servo is around 1600 or so, and the figure that you see in the left, the servos here are 1600 so, and the mounts are usually 100 and 100 200 rupees. But we can also fabricate the mounts in our lab. And similarly, the model that you see on the right, this entire model has been actually the 3D printed, and the servos that are being used are something like 500 600 rupees servos. The carbon tubes are also easily available. So basically, to change a fixed or a conventional quad to something like this servo mounted propeller quads is very cheap as compared to the total cost of the quad that one can account for. Now, once you do this, in this case, what we have done is the servos can make these rotors rotate with their axis being along the arm on which they have been mounted. Okay, so if you see in this diagram, I have marked something known as this XB axis. Okay, so this particular servo can essentially make the rotor rotate about this particular axis, and the same can happen for the opposite one. It is along the opposite arm, and similarly there are two mountings that you have along the YB axis as well. Now with this, all the 4 servos, if they are independent, so the controls that I have is the angles that I can maintain, which are 4 angles that I can maintain, and the speed of the rotors, which means the amount of thrust each rotor can produce. So I have 8 controls now, and I need to control X, Y, Z, which is basically the position, and the attitude, which is again a 3-state. So for 6-state control, I have 8 control inputs. So this becomes an overactuated system, which means now I have the capability of controlling the position independent of the attitude. Unlike the conventional quad rotors or the variable pitch quad rotors, where you want to, let's say, go forward, you have to basically pitch down, right? So your nose has to go down so that you can go forward. Why do we do that? Because we need to generate a force in the forward direction so that it attains a certain velocity which results in this motion. Similarly, if you want to go left or right, you have to roll accordingly so that you generate a component of force along the desired direction. Here, instead of doing that, you are basically tilting the rotors. Okay, so you can maintain any attitude that you want and tilt the rotors accordingly so that you can go in a desired XY direction. Okay, so this tilting of rotor helps us in achieving this additional degree of freedom. So if you see now, the change that we have in this flow is now the position and the attitude are decoupled, and depending on the thrust, maximum thrust that these rotors can generate, there is a range of attitude up till which the position and attitude can be decoupled, after which they again start having this coupling effect. So our entire thing is based on the range where it can be decoupled. Now, one reason that got interested to look into such designs where attitude can be decoupled from the position control was in case of conventional or variable pitch cords where the position and attitude states are coupled. If you are trying to survey something and there is a fixed onboard camera facing downstairs, then as the vehicle moves, what happens is the camera's view tilts. Okay, so you need to correct your images accordingly. But in this tilt augmented rotors, what happens is even if you are in motion, because of the tilt, you can still maintain attitude so that your view remains parallel to the ground and you need not make those corrections to these images that are received. Similarly, if let's say you are inspecting a bridge, so in case of bridge inspection, as you go parallel to the bridge, you have to in case of a conventional pod, you basically have to roll or pitch depending on your motion, and that is how the camera that is mounted to inspect this bridge will also tilt. So the camera view does not remain parallel. And now with this, you can maintain a parallel attitude to the bridge while doing your inspection and while having this XY motions. So this is a schematic where it shows how the forces are now not only along the rotating axis of the propeller, but not along the axis perpendicular to the body frame, but they can be at any angle corresponding to this body frame. Okay, but in the experiments that I'll show you, to start with, what we had done is we had coupled the angular motion of these rotors, basically the tilting of these diagonal rotors together. So as I have labeled, alpha 1 and alpha 3 are representing the angles by which the rotors are tilted, and this alpha 1 and alpha 3 are always same. Similarly, alpha 2 and alpha 4, which are diagonally opposite rotors, their tiltings will always be same. So now, because of this coupling, instead of 8 control inputs, we finally come down to 6 control inputs. So we have 6 control inputs and 6 states to control, which means it's a fully actuated system that is being simulated. So hence, the position and attitude decoupling can still be done. So this is an individual layout of the 4 mounts. So this was a preliminary diagram, preliminary CAD drawing that we had for one of the quads that was built around a wooden frame. So this was the servo mechanism that was used. This is the rotor plane. And with this motion of the servo, the rotor plane can tilt. So the thrust need not be along the perpendicular z-axis of this particular quad. So this holds for all the 3 rotors. So now the forces that are generated by these individual rotors, if it is resolved in the quad rotors frame of reference, so it will start having components. Okay, so one component is along the so there is no component along the x-axis, and then there are components along the y and the z-axis. So these components, the second components are usually responsible for the yaw and the motion in X and Y. So this, these forces that have been resolved, and this are basically MIs are the moments that you get because of this rotation of each of the rotors. So this are essentially useful in controlling the yaw, and this can be varied to control your roll pitch. And all of this again together we'll see in the model that they are able to control the forces along X, Y, and Z, and as well as the attitude together. So this is the attitude dynamics that we essentially end up with. So here the representation has been given in terms of quaternions. So Q is the quaternion vector that represents the attitude of the vehicle, with the capital omega being the angular velocity. And this is the angular velocity dynamics that we have here. mv is essentially the moment that is being produced. So there is one component which comes up because of the thrust that is being generated by the rotors, and one component because of the moment that is coming because of the rotation of the rotors. Okay, so there are these rotation matrices involved. Why? Because this Fi and Mi are essentially the forces as you see in the rotors plane. They are translated to the quad rotors frame, and this is the rotation matrix that is being used to translate the forces into the quad rotors frame. So this gives us the actual dynamics that is there in the quad rotors frame. Similarly, if we see the position dynamics, the accelerations along X, Y, and Z. So in the as seen in the inertial frame is this, where this TB is the thrust, or TB is basically the force vector that we see in the body frame, which is nothing but the combination of all forces translated from their respective rotor frame to the quad rotor frame, and they are summed together. And of course, we have the gravitational force in play. So from here, if you see the Fi's and Mi's had been resolved along the axis, along the body axis that we had. So the vertical and the horizontal components of both forces and the moments are essentially responsible for not only generating the moment required for controlling the attitude, but also the forces that are required to move the quad along the XYZ axis in the inertial field. Now, so we have three force components in the body frame, which is TB1, TB2, and TB3. And then there are three moment components also in the body frame, which is MB1, MB2, and MB3. So the TB3, MB1, and MB2, they are MB1, MB2, and MB3. These four are mapped to the rotor speeds, whereas the remaining TB1 and TB2 are mapped to the tilting of the rotors. Okay, so this is how the control allocation has been done. So whatever controller we design, they will give us this moments, which is MB, and the forces, which is TB, that is required to maintain a certain or follow a certain command, like following a certain reference trajectory for position and a certain reference trajectory for the attitude. So the control law gives us this. Now these are to be realized in the form of angular speeds of the propeller and the tilting of the propeller. So this is a So this is a rough map that tells us how it can be done. So this is one of the allocations that we had done. So the third component of the force and all the moments together tell me what is the angular velocity that I need to maintain for all my rotors. And the first two components that I have are being mapped to the servo tilt angle. So this essentially tries to say that the first two force components are responsible for somehow movement along the x-axis. So I'll try to realize this by tilting the rotor planes, and the remaining, which is for control of the Z and the attitude, I'll realize it by controlling the rotor speed. So this is what the rough map looks like. However, there can so what we have not put here are basically the constants that are associated with the rotor speed and the force and the moments that are generated because of certain speed. So they can be included in place of this numeric values one. But this gives us a rough idea as to how the allocation can be done and how the angular speeds and the tilts of this rotor are associated with the forces and moments that have been generated by the controller. Okay. So one such controller that can be designed given the dynamics that we had is this. So this is a quaternion based controller. So we have the quaternion error vector and the angular velocity vector that we have. So this is trying to follow a quaternion vector whose desired angular velocity is 0. So this is essentially a structure that replicates a PD controller. So this angular velocity is like the derivative of the quaternions. So this is the D gain that you have, and this is the proportional gain that is there. So this is responsible for generating the torque. And then this T1, T2, T3 are nothing but the desired accelerations along the inertial X, Y, and Z. So this comes from the errors that we get along X, along Y, along Z. So this is basically a PID controller that has been emulated. So once we get this force components, these 4 components are in the inertial frame, which are then translated to the quad rotor frame. So in the quad rotor frame, we get the desired thrust, the desired force vector that we should have. And finally, the moment in the quad rotor frame and the thrust in that we have got in the quad rotor frame, this together are allocated to the angular speeds and the rotor tilt angles through a similar allocation map. Okay. So I have one, I'll show you one preliminary test video that we had for this. So if the video is visible, so you can see that the diagonally opposite servos are coupled, so they are moving by the same angles whenever they are being commanded. So here the aim is to go to 4 waypoints. So the waypoints are placed at the corners of a rectangle that has been designed while maintaining a 0 altitude. Now, this motion is not possible in case of conventional quads where you cannot change the direction of you cannot change basically the direction of the thrust smoothly as opposed to this tilt augmented quad. Okay, so this is my PhD student who ran his preliminary experiments on such a system. He has graduated now. Okay, I think the quad is far off. I will have some other videos where you can see what actually happens. So I'll show you the plots. So for a conventional quad and for a tilt rotor quad, we used similar waypoints. And this is how the path following looked like. So if you observe in tilt rotor quad, there are a little overshoots. This can be done away with if the gains are tuned appropriately. But the takeaway is in both cases, in case of conventional quad and in case of a tilt rotor quad with similar parameters, they are able to trace the path and they are able to cover all the waypoints. So they can go from waypoint 1, 2, 3, 4 in both cases. Now, if you see the attitude that was there for roll, if we compare the roll angles, let's say, when it is in motion, in forward motion, sorry, this is the pitch, this is the roll angle. So when it was having a motion along the y-axis, if you observe the roll angles, they have gone somewhere close to 30 to 40 degrees. Okay, so this, the highest one that you see is 40 degrees, and on the negative side, the roll angles have gone to as high as minus 20 degrees. Okay, so this indicates that the quad rotor, conventional quad rotor that we have, needs to roll so as to generate these forces and move in a particular direction. But if you observe, in case of a tilt rotor quad, the commanded attitude has always been 0, and the actual attitude that we got was somewhere close to plus minus 3 degrees. This was basically, I mean, ideally it should be 0 degrees, but because of some design asymmetries, this turns out to be plus minus 3 degrees. Now with plus minus 3 degrees in case of a conventional quad, I mean, such motions will not be possible. Okay, so this is what we have. So this essentially tells that the roll component has been completely decoupled from the horizontal motions that you have. A same behavior or similar behavior is seen for pitch as well. So in case of conventional quads pitch, the pitch angles go as high as minus 40 degrees. And on the other side, they go as close as 25 degrees. But in case of a tilt quad rotor, you see that the pitch angles are very low. And at times there are high pitch angles. This is coming because of certain disturbances that wind disturbances that we had during the flight. So if you see this, then I think the maximum that has gone is plus minus 5 degrees, which is very low as compared to what we had for the conventional quads for the same waypoints and the same trajectory that was given to these particular quads. Okay, so this essentially this experiment demonstrate that the actuation change that has been done, or the additional actuation that has been made available to this conventional quad has actually helped in this decoupling. Okay, now with this fact that I can fly or I can have a motion while maintaining a zero attitude, why we did this was we wanted to see if we can land a quad rotor on a moving platform, and that platform need not be moving along a straight line but can move in circles or any other trajectory. And to make things simple and to avoid the installation of gyros usually which are used to mount the cameras, we went for this alteration which we thought was cheap enough to do. Now once done and with this promising experimental results, we then attempted autonomous landing of such a quad rotor on a moving platform. So for moving platform, we had a ground vehicle available with Dr. Mangal Kothari and Aero. So we used it first we tested it in indoors with a indoor positioning system, which is the Vicon setup that is available in the aerospace department. So we tested it there, and then we went and tested it in outdoor environment also. So I'll show you all the results here. So what we had done here is we had a down facing camera which was connected to a Intel NUC board. The Intel NUC board was responsible for processing all the image and identifying the pose, relative pose of the quad with respect to the platform that is there, and finally sending out the commands to the onboard flight controller, which was basically a PIXOP flight controller. The PIXOP flight controller was generating the control inputs, which was controlling the tilt angles and the propeller speeds. So now, yes. So what was the challenge? The challenge is usually the landing platforms are small, so it has to be as precise as possible. And we tried this with a conventional quad, and it didn't work. It always failed. So what we did was we used this, and every time it gets from the image that it gets for the moving platform, it is able to generate a trajectory, and the controller tries to estimate the velocity of the moving platform from this trajectory, and using that it was able to command the quad rotor to maintain a particular velocity and a position with respect to the moving platform, and simultaneously decrease its height so as to land precisely. And this was all possible because of the tilting nature of the rotors. On the moving platform, we used a compound Arupa marker. There are various compounding that can be done for Arupa markers. This is one compounding that we have done is we had used three Arupa markers placed side by side. So the first Arupa marker is something that would be clearly visible from a good height. And then as it starts landing, this first Arupa marker would go out of will not be completely in its view, So that is where the second ARUCO marker comes in, which is basically somewhere in the intermediate stages. And finally, when it is close to the moving platform, the second one will also not be completely in its view. So the size of the third ARUCO marker was decided accordingly, so that when it lands, the ARUCO marker should still be completely in its view. This is a compounding that we had done. The other compounding ARUCO markers that are available online and people have talked of are basically fractal based ARUCO markers or concentric ARUCO markers, so that as you come down, the ARUCO markers which are inside become more and more visible. But this was simpler for us to settle to, and that is why we used this. So this is the view of the ARUCO marker that was placed on the moving platform. So below this flyboard, there is this ground rover that we have, which was an autonomous ground rover, and the paths were commanded to it directly. They are programmed in it. And this is the ARUCO marker that we had printed in the lab. So this is the big ARUCO marker that we have, and this one is the smaller one. So if you see, the smaller one is not clearly visible, but if you see on the right hand side image, after it has landed, the smaller one is actually clearly visible, whereas the other ARUCO markers, this black line is for the bigger ARUCO marker, and this black line on the top is for the smaller ARUCO marker. Okay, so they are not visible at all, but the ARUCO marker, which is the smallest one, is visible even after landing. So this is how it has been placed. And also to ensure that the landing is precise and the platform always remains in view, we had proposed a landing zone, which is basically like a cone. So the base of the cone, which is this, was the size of the ARUCO marker that we had, and from that we had extended. So the height of this landing was decided, based on which I think this cone came out to be 0.8 meters at the topmost height, and this topmost height was 1.5 meters. And then we had a safe zone of 0.27 meters as well. So whenever the quad lands, it has to be always in this particular zone. So as the height decreases, if somehow the quad comes out of this zone, then it will again reset itself and go up and come on to this marker again, track it, come on to this marker, and then start reducing its height. And then once it is again at 1.5 meters from the ARUCO marker, it will execute its landing. Till then, it will be in a tracking mode. So this is the video graph from the indoor experiments that we have done under the Vicon setup. So here, once the quad is at a height of 1.5 meters, it started executing its landing. So it continues to track. So as it lands, it continues to track the platform, and finally it lands. And if you see this, I don't know whether it is visible here or not, but in the videos it will be clear. So that it has landed directly on the smallest ARUCO marker. So the camera is would be having the view of the smallest ARUCO marker that we have here. The trajectory that we had was this. So the dotted trajectory is basically the path of the vehicle that it was going. So it was executing a circular motion here. We manually launched the quad, and at this point we put it in autonomous mode. So this is where it started to track, and it tracked for a certain time, and after which we asked it to execute landing. So since it was at a height of 1.5 meters, it started to execute this landing. And as you can see, the height keeps on decreasing, and it is at this point where it lands, and it continues to move along with the ground rover. This is the video for the circular motion. So here the ground vehicle is in circular motion. So it is, the frames are basically from right to left. So the quad rotor starts landing and finally lands at this particular point. So I'll show you a video that shows our experiments which we have done for both indoors and outdoors for landing on this moving platform. So this is the rotor. This is the servo that we have used. These are typical servos which are used in this hobby grade robotic manipulators or hobby grade humanoids. So we have used those servos here for demonstration. And the Intel NUC board is here, to which the camera is connected. Camera is at the bottom. And then in this space, we have the PICSOC and the power distribution boards. Below there is a battery as well to power up this entire thing. And the gray markers that you see here are essentially points or marker points for the Vicon system. So this, though the Vicon system is not being used to do this job, the Vicon system was used to compare the trajectory of this quad with the, so Vicon's output was considered as the ground truth here. So this is the vehicle which is executing a circular motion. So the quad rotor is tracking it here. And now it will start to land. So with this, we thought we'll go outdoors. So in outdoors, we, thanks to the runway that we had, we did two experiments, one at a speed of 15 kilometers per hour. So the quad could basically track the vehicle at 15 kilometers per hour, and then it starts to land once we command it to land. So it's still tracking. So the tracking is based on the bigger marker. Now it has started to land. So you see the ARCO markers change, and finally it lands on the smallest point. So this is with 15 kilometers, and the similar experiment was repeated for a 20 kilometer vehicle, to 20 kilometer per hour vehicle speed. We're still tracking. Now for this tracking, there is no communication between the landing platform. The GPS information is not being used. It is just based on the ARUCO marker that has been done here. So now those demonstrations were for cases when the diagonally opposite rotors were basically had coupled tilting, so they tilt in the same direction. But these servos are capable of getting different tilt commands, so the control allocation now changes. Okay, so the the three force components and the three moment components can be allotted to 4 rotor speeds and 4 tilt angles, and this actually gave us freedom of even doing better. So here, when the coupling was there, what we saw was we can fly at a 0 altitude and go to any position. But with this 4 tilting now available, so the tilting not being decoupled, what we could do is now we can fly at attitudes that may be counterintuitive for conventional quads and still go to or still do the same waypoint missions. Okay, so basically for a conventional quad, if you want to move forward, you have to pitch down, but in this case you can move forward while pitching up or having some roll. Okay, you can have some roll and yet you did not move along the y-axis altogether. So this is an experiment that we started with. Is we gave the roll and pitch to be sinusoidal angles, and we asked the pod to hold the current position. So what you would see is it does the roll and pitch sinusoidally, so it basically circles, and the deviation in the x and y is, I would not say 0, but they are very less as compared to what it would have gone for a conventional pod. So this is not an unstable operation. This we are deliberately giving, so it is able to land while doing this oscillatory attitude. And for safety, what we had done was we had kept a height of, I think, 2 meters above the ground. So once it is above 2 meters, this attitude the sinusoid attitude would be given, and once it is below 2 meters, it will be basically fixed stable attitude so that we can land it in cases of emergencies. So you see here, this is a sinusoid given along one axis. So if you see the rotors here, the rotors are also basically changing their tilt angles. Now, why is this happening? Because the position has been asked to be constant. So once it rolls, there is a force component being generated. That force component is being countered by this motion of this rotor, the tilting motion of this rotors. Okay. So this is another flight demonstration where both roll and pitch are being sinusoid, and the amplitude of the sinusoid for roll and pitch is basically minus 20 20 degrees. With a time period of roughly 15 seconds. So this is one that we had done with a quad with frames that are available. So these frames are basically something like the Lego kits, but are made of aluminum, so you can make quads of different sizes. And this is the one that we had printed. So this is basically a quad which is around 200 mm. The entire frame was printed in the lab and has very small components. So in case of crashes, we are immediately able to reproduce it. So here also the angle was commanded to be with an amplitude of 20 degrees and a similar time period of oscillation. So the deviations that you see are very less as opposed to what one would have seen with respect to the conventional quad rotor. So in case of conventional quad rotors with this much, you would have essentially seen a circle kind of big circle kind of motions, because 20 degrees is a good enough angle to move it along X and Y with high accelerations. So I think I finished early. So thank you for your interest in this talk. These are a few of the quads that we have assembled in our lab, some for practice, and we have also worked on the variable pitch quad rotors. What we are currently aiming is the variable pitch quad rotor, as Professor Abhishek was also mentioning, is a single engine driven quad rotor. So it is designed for that purpose, where you can change the blade pitch angles. We are trying to see if a tilt quad rotor can be designed so that it is again a single engine based quad rotor, so that with this tilting capability, now the position and attitude can be decoupled. We keep on posting our experimental videos on our lab's YouTube channel, which is given here. So thank you for your interest. If you have any questions,
yeah, this is Vijay Kumar here. I can ask a question.
Sure, sir.
Yeah. It was a very good presentation, very interesting controls and various things. Thank you for that. One of the very challenging thing is to land a helicopter on a ship. Okay.
Yes. Yes.
Ship, you know, has got pitch and roll and heave. Heave is the collective up and going up and down. Okay.
Yes. Yes.
It has got all three motions, and there are what is called the C state 1, 2, 3, 4, 5. That's it. Okay.
Yes. Yes.
What I would probably a good work experimenting that you should do is you should have a small setup in the lab.
Sir, your voice actually becomes very.
You should have you should have a small you should have a small setup in the lab, which can using some hydraulic jacks, etc. You can always have a platform which can do pitch and roll and then also heave, going up and down. And if you can land that and then try that, that will be a very interesting thing. And we have tried, we have found that it is very difficult to do that. We did see actually using advanced light helicopter, we did hover at a point.
Yes.
Okay, actual hovering at a point using an autopilot itself is a challenge. what you have done is a pretty good job, but I feel you should try, but for Navy, it will be a very interesting project. Okay.
Yeah, so
Risk
actually
is very high. Let me tell you, the risk is very high when you land on a Navy platform, because if you hit the ship which is by the side, it will be a catastrophe. So that is a good experiment if you can do that.
Yeah, so we actually started this with the thing in mind that the platforms that usually we'll be landing, whether it's a ship or a moving vehicle on a uneven terrain, that the platform will never be flat. It will always be having this roll and pitch, and in case of ships, it will also have this heave. So with the tilt design that we have, the one that I showed you at the end, where we can have arbitrary attitudes and arbitrary position control when all the tilt angles are decoupled. For such quad rotors, I'm confident that we can land on such platforms. I have to just demonstrate that yes, we can do it. But given that attitude decoupling, yes, we can. But I think in case of helicopters, this attitude decoupling is not possible with respect to the position. So it is again a difficult problem, but I'll be happy to work on it. And I think Professor Abhishek's team is already working on such a problem, if I'm not wrong.
Actually, that is correct. I mean, so I mean, there is a student from electrical department only. There, the focus is more on the computer vision side. The main advisor is actually Professor Venkatesh in electrical, and we are trying to do something similar, sort of continue Dr. Sahu's work, but his focus actually was with this tilt augmented quad. So we are now trying to do the similar kind of thing with helicopter, with using a moving camera, where the camera actually is actuated so that the camera's view always remains constant. Whatever my vehicle does, camera will continuously keep seeing the Aruko markers and do something. So that kind of work is being done in simulation already. We have done some things in simulation. We will be soon starting with the experimental work on that side. Yeah.
Okay, that's good.
And we are taking help from, of course, Dr. Sahu also. So he's also together in this actually. So he, Mangal, I mean, all of us, I mean, are anyway working together in different problems at different times. Yeah. So.
Yeah, I forgot. I mean, this work on tilt was actually done along with Mangal. So we worked together on this particular problem.
Yeah, I mean, actually, I had been showing this video for quite some time at many places, but I had never seen the technical work behind it. So today I'm very happy that I also got to see the whole work. But it is a very, really good work actually. And I knew that, I mean, Dr. Vijay Kumar sir will actually ask this question regarding helicopter landing on ship decks.
Yes.
Yes, sir. So we are actually already doing something. I mean, although we don't have any funding for that, but I mean, we are actually working at whatever pace we can, trying to solve this problem, because there is a PhD student working on this actually.
Okay.
Yeah. And also to add to Abhishek's point, as I said that the existing, I mean, quad rotors are becoming really popular with in various places. And as I mentioned, that augmenting this with tilt capabilities is going to be cheap. I mean, we did it for something probably like it would be something like 7,000 rupees upgrade or something, along with all 3D printed parts. So the point is, any quad rotor can be converted, and if can be done, then of course that landing on platforms which have roll pitch and your along with XYZ, which can be basically emulated using the SWOT platform structure, I think that should be doable. I'm actually aiming for that, for using a tilt quad. So
I mean, Dr. Sahu, I mean, you should actually also consider now putting wings on your tilt quad.
Yes.
Yeah. So once you do that, then I mean, it becomes a far more potent vehicle actually. Then you are fully exploiting the capability of tilting.
Yes.
So,
in fact, we have theoretically proven that. I mean, we have found out some conditions on the amount of force that this propeller should generate, so that it can actually flip, unlike variable pitch quad rotors or helicopters, where you can lose your attitude when you flip. That won't happen in such cases. In tilt cases, you can flip very smoothly, and you can transition through any attitude that you want. It can be a very smooth continuous transition. So the vision here was usually during obstacle avoidance with conventional vehicles where the position and attitude are coupled, you have to plan both the position and attitude for obstacle avoidance in very thin scenarios. But here you need not couple them. So you just plan your position, the attitude gets coupled depending on what is the width between the or gap between the obstacles. Just so you can plan them completely independent of each other.
Okay.
Any other questions, comments? Koda sir, I mean, are you there?
Yeah, I'm there.
Great, sir.
I was just I was listening. I thought it's a very interesting work, but I was only wondering. I think you have already made a comment on how we can take it to the next level. That's what I thought it would be something good. And I do feel we should do that. Then what happens? We will be able to then solve the problem of a ship on a 6 degree of freedom motion and a helicopter or a quadrocopter or any one of them landing in such condition. But tell me, if you have a camera which is what you call stabilized, will it help to do better? On the rotorcraft or there, suppose you have a stabilized camera which is pointing towards the ship, will it help to do a better job and more accurately, or it is still an uncertain game?
No. For example, with this decoupling that we have of the attitude from the position, usually when you approach a ship, let's say with in case of a quad, when the position and attitude are coupled, you would slightly tilt downwards, right? So the propellers might hit. Here, your tilting would be very less as compared to the body being tilted directly. So your propellers hitting while landing would be very low. So the camera can still point, but the chance of losing a vehicle might be reduced. Because usually what happens is when you land and if you hit the what we have observed in our experiments, when they fail, it always first hits with the propeller and the tip basically takes it off very dangerously from the ground. So if that can be avoided, at least those accidents can be avoided, then I think
I understand recently Navy has raised a request for a proposal where they are talking about what you call vertical takeoff and landing vehicle, which could what you call with the endurance of almost 10 hours. I don't know, Abhishek must have seen that.
Yes. Actually, ARDC is talking to us. I mean, we are discussing with them to see, I mean, what can be done for that.
See, a typical helicopter, I mean, manned, unmanned, I mean, you are talking of unmanned, having an endurance of 10 hours seems to be not a practical solution.
Sir, actually, there is a small tail-sitter vehicle called Flex Rotor, built by an American company, and it is not even meant for defense application. It's meant for actually tuna fishing. That actually has it's almost like, sir, I mean, our helicopter taking off like a tail-sitter and becoming an airplane, that small mini helicopter, and that actually has claimed endurance of 22 hours.
But tail-sitter.
25 kg, sir. Tail-sitter.
That
like
means it is a conventional aircraft, but a tail-sitter. That I can understand it can do, but a helicopter, I thought it will not be possible.
True, sir. True. I mean, it has to be a winged vehicle, actually.
It should take off in a vertical fashion, and then it should what you call come to a normal position. Then it can take advantage the aerodynamics of a conventional aircraft. Then the endurance can be high.
Right, sir.
But a pure helicopter configuration having 10 to 12 hours of endurance, to me it looks to be quite tough.
It is tough also, sir, and it is not going to give us a practical solution.
That is the point. But I don't know why Navy has come out. Of course, they didn't say it should be a helicopter. They're only telling it should be a vertical takeoff and
Yes,
it should have an endurance of 10 to 12.
Right.
I think the configuration which we should is a vertical takeoff, and afterwards it should become a conventional
Right, sir. So
aircraft.
it
That
can
is the
be
only way you can give
yes,
that
yes.
kind of endurance.
Yes, it could
Yes,
be a
sir.
lift.
These are 10% time helicopter. Rest of the time it is fixed wing, sir.
Yes,
Yeah, that
yes.
is the point. So
That
it
should be
should
like
be a
that
fixed
only,
wing
otherwise,
aircraft, which can be
you
a
can't
tail
get
sitter
performance.
or a vertical takeoff using
Right,
a
right.
vertical engines and all that kind of thing. We can try 2-3 alternates. I
Yeah.
thought that way we will be able to do. Okay.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
I hope. I don't know who is going to bid. I don't know whether Abhishek's firm is bidding.
No, sir. Beyond our ability, I mean, only HAL can do, sir, something like that. Yeah, that is because the requirement of payload and all, it is going to be almost a 1-ton vehicle, sir.
It's quite a long bit. They are talking about what is the payload they are talking?
Sir, almost 200 kg or something, sir. I mean,
200 kg.
Something like that, sir. I
means,
mean, I'm not sure.
at least 1:5. 1:5.
Right.
Only
Right.
good
I
thing
mean-
is it is at sea level, because you are
Yes, yes,
if you say I lead that at a higher altitude, wo fir gadbad ho jayega.
Becomes very, very difficult problem, sir.
Yeah,
Very
yeah,
difficult.
yeah, yeah. I don't know. I hope HL is bidding or they are not bidding.
Sir, ARDC is very keen on that. I mean, we have had few meetings on that. So they are
You had 2
currently
meetings.
progressing. Yes, sir.
But HL, ARDC is looking at it, or helicopter?
ARDC, sir. ARDC.
Ah,
ARDC is
it
looking
should
at
be ARDC, not helicopter.
yes.
Design bureau,
Yes,
but
yes.
then they have to know how to do this transition from vertical to horizontal. A fair amount of control aspects they need to look at it. Anyhow, it is good to thank you.
Sir, you are saying, sir, something, sir, Vijay Kumar, sir?
It should be ARDC only because it
Yes,
is
sir.
10% only.
Yes, yes. Because last time, sir, I mean, our proposal from ARDC went to RWRDC, and RWRDC said, I mean, we are not going to support this.
But
They said, Look, but,
they will not be able to handle the controls easily.
Yes.
no,
yes.
I
It's
think
a challenge,
it can be ARDC with support from IIT Kanpur.
Yes, yes.
I'll
that
put it that way.
Yeah, right.
That would be
There is one question, I mean, Dr. Sahu, I mean, for you that how would a multi-copter with shifting CG work by shifting the drone body angle?
That I don't know. I don't know how you shift CG. I mean, I'll
So
be really-
actually, this kind of vehicles have been built, I mean, in 1980s also, manned vehicles.
yeah.
Which are
So-
controlled even in the this recent last decade also, some were built in Japan and all, where they had a fixed pitch coaxial helicopter, and the control was achieved by CG shifting. The guy who is sitting, he will bend, he will move like this, he will do something, he will do something actually, and by shifting the CG, he will try to offset the thrust vector and get the maneuver from that. So it's not a very practical and efficient way of doing thing actually here. Doesn't give you a lot of advantage other than some simplicity in the control, but it's not very maneuverable, not very practical. That is my understanding.
So good. Hey, today went up well. Very excellent talks. Thanks.
Yeah,
to-
all the 4 talks are really great, and
yeah,
tomorrow
very,
also
very
some
good. Very good. Very good. Okay. So all the best
tomorrow
for
also,
tomorrow.
right, so we have some very
I will
nice
be able
talks
to
lined
join
up
in
for
the
tomorrow.
beginning, but I will join somewhere in between. Okay.
Sure, sir. Sure.
Okay.
Absolutely.
Okay. Thank you.
Thank you so much. Thank you, everyone. Okay, yeah. And Deep, I'll answer your question later. I mean, we can discuss this, I mean, offline. Okay. So I'll stop the recording and